Welcome to Chapter 1, Section 1, Analyzing Data for AP Statistics. Today we're going to be talking about exploratory data analysis. This is the practice of taking your data, graphing it, getting some numerical summaries, and then looking for patterns or deviations from those summaries. We have two types of data we're going to be focusing on: categorical data, which shockingly enough is when your data has categories. So the example below is we broke up age groups into categories and then counted how many people fell in that category for owning MP3s. Uh, and then we graphed it in really two of the main ways that you can do categorical data, which is bar chart or bar graph and a pie chart. We would use mostly uh, bar graphs because it's easier to see distribution patterns in bar graphs than in pie charts. But pie chart is another way to communicate your information because a lot of statistics is communicating what you find to a larger audience. One subset of a bar graph is the stacked bar graph. And this is when you want to add another category to your already categorical data. And you can take the values and stack them on top of each other. So in this example, we have the quarters of the year, and then we have how many hours per month people used Facebook, Instagram, Twitter, LinkedIn, and then you can compare those to each other. Normally, stacked bar graphs are changed to percentages, so then they all end at 100%, and it's a little easier to compare the different categories to each other. But this graph was done with just total hours. So you can see that quarter one, you used more hours for LinkedIn than you did, let's say, quarter three, quarter four. And then you could go and say, why would that be? Do people more often look for jobs because LinkedIn is used mostly for networking? And so did people look for more jobs in quarter one, and that's why they spend more time on LinkedIn? So then you can go investigate, what does this data tell me? One other type of plot that's new to AP statistics this year is the mosaic plot, and that adds yet another piece of information to your graph. It helps you see the sample size of your different groups. In this graph, we have students and teachers were surveyed to see their favorite math class. And then it was graphed in a stacked fashion with the percentages on the left. Now, you may think that the different categories are widely different if we didn't look at how many people were surveyed. So the width helps you see proportionally one group to the other. So let's say the students were 5 times as wide as the teacher's graph. So we could say, I'm just going to make this up, let's say there were 500 students surveyed, then probably 100 teachers were surveyed. And then you could say, oh, okay, so numbers wise, it may not be that different how many people liked pre-calc in teachers versus students. It's just proportionally the total number is smaller for teachers. All right, that's all we have with categorical data. Now we have quantitative data. So that's when a variable takes on a certain value. If we went back to the age example, that could be when we just have ages of people, we don't group them into categories of ages. And we have many more ways to display quantitative data. The first is a dot plot. So here we have hours per week watching TV, and each of the dots represents a sample. You can kind of see it's mostly clustered around 0 to 24. But there are these values out on the edge on the right-hand side of the graph. And those could be potential outliers. Notice I said potential because until you run a test, which you will learn this chapter, uh, you can't say for certain they're outliers. So you always want those modifier words, potential, approximately. We'll hedge our bets a lot of times in statistics if we don't have a for certain answer. This is also what you would call skewed to the right, because if I were to draw just a line on over the graph, you can see it tails off to the right. And it's called skewed to the right because this value here, this big one, and for some extent these over here as well, they're pulling the mean towards them. They're skewing that mean towards those higher values when really it should be a lower value if it wanted to represent the data set. But those upper values are skewing it. Right. Then we have a stem and leaf plot. And if you haven't seen these before, the stem is on the left, the leaf is on the right. These red numbers are just counting how many data points there are. You don't usually put them as part of the graph, so you can ignore those. The main thing you need here is a key to tell you how you put your numbers back together. Because I could, without a key, assume that it was the 8, the line, and the 0 represents 8.0. So without the key, I don't know, is this 34, 34, 35? Is it 3.4, 3.5, or is it something like 34,000? So you always need your key there as well. Then there's a variation onto the stem and leaf plot, which is the back-to-back stem and leaf plot. And that puts the stem in the middle so you can compare two different pieces of data. Usually they're connected somehow. That's why you want to compare them. So this is pulse rate before and after exercise. It's missing a key, so I'll write it in since I know pulse rate is generally in the 68 area. That must be what they mean. So here you can see before exercise, obviously clustered down 60s, 70s, and then after exercise it is higher. And this one person who got 146 is a little concerning, but that would be your distribution. You want to see what happened with that piece of data. Because one point is, even though this could be an outlier, again, notice I said could be, it may still be a valid piece of data, but if you get an outlier, then you want to go back and make sure, was there an issue with acquiring that value? Did the clock break? Was there something weird with the exercise equipment or the environment? So outliers aren't necessarily invalid pieces of data, but there's something that you want to make sure that they are okay. And then we have a histogram. You notice there's a bar chart here, which we talked about earlier for categories. The big differences between the two is bar charts don't have gaps and histograms don't have gaps. So a bar chart does have a gap, and that's because they're not continuous. So China does not flow into the United States. Whereas histograms, the numbers are continuous, so you connect the bars. And that's really the only difference. So bar charts are for categorical data, histograms are for quantitative data. Otherwise, the looks are the same and plotting them are the same. And lastly, we have the box and whisker plot or box plot, depending who you're talking to. These are useful more when you have more than one. So one box plot by itself, it can show you generally what the distribution shape is like, but it's when you put them on top of each other, like this business and law salary, is where they become useful because you can compare mins and maxes and medians. And we'll go through how to draw one if you haven't done one of these yourself in the next section. But one piece of information that's useful is each section has 25% of the data points. So what that helps us with, oops, can't read that, 25%, is if this one area is smaller than another area, even though they both contain 25% of the data points, it means that this area that I'm drawing the arrow on right now, that means that data is more tightly packed together. So the data points are closer together because they don't take up as much of the number line to get 25% of the data points. So that means between like 69 and 75, there's the same number of data points as between 75 and 85. So you have the same number in a smaller span, so your data is more condensed. The other thing you can check is if it looks skewed. So if like this tail went off all the way down to there, it's probably skewed to the right because you have 25% of the data. It means there's probably one data point down here that is an outlier, that if you have the data points, you want to go and check that data point. Most software and calculators that can graph will have an option to do box and whisker plot with the outlier kept in the data or the outlier taken out and marked with a dot or an X. All right, so let's summarize our information before we do two last things. Exploratory data analysis. What should you do? You always want to plot your data first. Whenever you get data, plot it. Then you're going to look at the shape. Is it symmetrical? Is it have one mount or is it bimodal? Is it skewed left to right? Is it uniform? And that's if your histogram is essentially, flat. You could have a little bit of a, it can't, with data, it's not going to be exact, but if it looks pretty much the same value, you could say approximately uniform. Outliers, and again, you'll have a formula, so you can either say potential outlier, or if you have used the formula, you'll say it is an outlier. One thing I put into this category is gaps, because G doesn't go into the nice SOX acronym of shape, outlier, center, spread. So that's if you had data and then there was no data in this area. You want to point out that like between 20 hours of TV a week and 35 hours of TV a week, that's a lot. There was a gap in that distribution. You always want to do it in context of your data. So hours a week watching TV, exercise, pulse rate, you always want to use the actual context. Center, we're going to talk mostly about two different measures of center, median and mean, in the next section. And spread, we're going to again talk about two main ones, standard deviation and interquartile range, in the next section as well. So you use that to kind of show how the data is spread out. All right, we have a couple cleanup things at the end here. First is, as we go into the next section, why mean versus median? Why do we use one versus the other? And from the summer reading of Ghost Map, there is a quote on page 84 about the 1842 life expectancy. These numbers are so shockingly low because life was especially deadly for young children. And it's still the same with life expectancy, even though our life expectancy has grown greatly from 1842. But still, if we say the average life expectancy, it's still not the best measurement. Median is probably a better measurement for life expectancy, and that's because looking at these curves, you can see they are skewed to the left, and that's because of, sadly, infant mortality. And then you have this big area where the values are small here, and then you get a lot more values in the later years of life. So the infant mortality pulls the life expectancy down. For females, the median life expectancy is 90, which is 7 years more than the mean. And for males, the median is 82, which is 3 more than the mean. So when you hear average life expectancy, you have to think that there's those smaller values from infant mortality that will pull the life expectancy value down. And basically, if you survive, you know, childhood, then the age you're expected to live to is a lot higher than the actual mean of the life expectancy values you hear on the news. All right, here's the couple quick things we want to clean up. First is percentiles, and you've probably seen these like on your SAT scores, if you've taken other AP tests, or if you've done any psychological tests, you hear what percentile you're in, and that's the value below which the observations are. So what I mean by that is the 20th percentile is the value below which 20% of the observations are found. So if you think about the median, that's your 50th percentile because it's in the middle. The formula is just your regular percentile formula. You're going to take whatever value you're looking at, you put your data in order, and you count how many numbers are less than the value you're interested in, divide by total number of scores, and you multiply by 100. So let's say like I had 1, 2, 3, 4, 7, 8, 9, 11, 9. All right, I have 10 data points, and I want to know what percentile I am if I scored a 9. So there's 1, 2, 3, 4, 5, 6. 6 values below that. So I am 60th percentile. All right, and the percentile can actually be graphed as well. And it's done with a graph called an ogive graph. I know it doesn't look like that, but that's how you pronounce it, ogive. And that shows you the cumulative frequency of a distribution. And it's probably easier shown than explained. All right, so here is an ogive curve of attendance at a Super Bowl. And you have the cumulative frequency on the y-axis and attendance in thousands on the x-axis. Always check what units those are in. And let's say I wanted to estimate the 50th percentile. So I wanted to answer this question, what is it? I go over to my 50th percentile and I draw a line to the graph, and then I draw a line down. And that will give me about 70th percentile. Oops, sorry about that. And so you want to make sure you convert it to your thousands, and you would get 77,000 people. All right, you can also do this the other way, and you can say, okay, what is the percentile then for 70,000? So I could go to my 70,000 there, draw my line over, and I'll say that's about 15th percentile. And because there's not a lot of definition on the axes, you will have to estimate on this. Depending on your example, how fine the axes are depends how much estimation you have to do. Please say approximately 15%. And the final graph is a time plot, which I think most people are used to seeing. It just shows the trend over time. A lot of times you'll see it stock market. If you go to YouTube channels, views, it'll show over time as well. But this is gas prices over time. And then what is interesting is to then go look up historically what was happening to make these dips happen. And then that's looking deeper into your data, not just looking at the pretty picture and going, well, the gas generally rises. It's interesting to see why did a certain point on your graph happen, or why did this spike happen. All right, so that is the end of section 1.1. I hope it was helpful, and I will see you in the next video.